where a lot of our class is. Joseph's there, Victor's there, Ryan's there, Colby's there, Toby's coming back. Oh, he's in honors camp too? Okay. David is also. All right, here we go. Number 10 should be C.
Oh, D.
Oh, yeah. I forgot D was on it too. Okay, number 10 is C. Number 12 is D. Number 14 is B. C and D and B. Where's grade, Toby? Number 22. Did you bounce? Did you bounce? You bounced. Hopefully you bounced.
Yeah.
Now, this one, kiddos, I don't even think they made a big deal about graphing, but you could have. You could have made sinusoidal axis 0, amplitude 3, period would be 1/4 of 2 pi, which would be pi over 2. We didn't talk a lot of yesterday, but cosecant and secant, who are they based off of again? Cosecant and secant?
Sine and cosine.
Okay, what's the period of sine and cosine? 2 pi, so what's the period of cosecant and secant? 2 pi. I don't think we wrote that down yesterday. Maybe we did. But to find the period of these guys, you would just take 1 over b times 2 pi, just like you do with sine and cosine. You see your vertical asymptotes and your bounce, bounce. Did you have to do a table? I don't think so, but I guess you could have. 28, cotangent. Did you have him decreasing? He didn't shift, so his vertical asymptotes were still 0, but the dilation did change it up using the period. Could you have done a table? I suppose. Did you have to do a table? I don't think so. I'll take questions in a little bit. Just make sure your sketches are good. You guys were doing these by hand, right? Or was it calculator? Yeah. Sorry, vertical asymptotes, in case you guys missed it. Vertical asymptotes would be every 2. 0, 2, 4, 6, 8, and 0, -2, -4. It'd be 2 ends when you guys solve. This one was calculator. Actually, both of them were. Just seeing if you could put it in. Nice thing is we practiced definitely the secant one yesterday. Just do 1 over 3 times, or you can do 1/3 times 1 over cosine. You had to get your cosine in there. Bounce with your zoom standard probably would have looked pretty good. Tangent's not too hard as long as you're in radians. If you're in degrees, radians so much easier because they're smaller numbers. What's going on with number 56? This one was kind of weird. They told you to solve. Why, if they told you to solve, why are they in their calculator? What's this supposed to be showing? Who's the bounce? Okay, good. So these ones, let's call this, still trouble. Somebody. Try this. So what's on? Oh, alright. Okay, that'll be our y1, and that comes from one side of the equation. So where does this line come from? y2. And question, when are two sides equal? Or when are two graphs equal? When they have, what are these shapes? Not quite intercepts. Intercepts are a snazzy way of saying intersections with the axis, but you're right with the idea. Intersections, yes. So you could have used your calculator to get intersections. If you had done that, though, these would be decimals. They wouldn't be nice, pretty unit circle ones. How could you think about the nice, pretty unit circle ones? Who's cosecant the reciprocal one? So, what would sine have to equal for cosecant to be -2 root 3 over 3? What had to be flipped? It's a unit circle, so it's 0, 1/2, or 2 over 2, root 3 over 2, or 1? Yeah, root 3 over 2. So this is what had to get flipped. So the question is, when is sine root 3 over 2 in the unit circle? At the pi over 3s, right, but oh, it's negative, so hold on, where is sine negative? Not here, not here. Sine is negative at those two angles in the unit circle. So that'd be 4 pi over 3 and 5 pi over 3. Oh, hey, look. They must have also told us some sort of restriction, maybe negative 2 pi to 2 pi. So not only did they go the positive 4 pi over 3 and the positive 5 pi over 3, but they also went the negative pi over 3 and the negative 2 pi over 3. So there are different ways of getting, but to the same exact location. That would have been a way of doing it with the unit circle. But you could have done it with your calculator. I just wanted to warn you, you would have had decimals. And the decimals would have equaled these answers. And get rid of all this. 58. They had you plug in and graph both of them. Long story short, it was the same exact graph because tangent is odd. Tangent is odd. Plug in a negative x, it flips the tangent. Tangent has origin symmetry. That's all that one was about. All right. What was weird that ended up happening with number 7? Yeah.
Yeah. Can you explain something?
It was weird. They had you graph two different guys, right? Two different functions. But what happened when you graphed them both? Same graph. Oh, that's weird. So there must be a way to write this nastiness as this. We talked about a while ago this cofunction property. Cosine of 90 plus x or cosine of, okay, what's another way of writing 90 in radians? Is the same thing as sine. Cofunction. Sine and his cofunction. Cosine. Sine and his cofunction. They're going to have the exact same answers. But sines happens at x and cosines happens at 90 plus x. So therefore, oh, sorry, negative. Sorry, cosine of x pi. What I'm talking about is 90 minus. Hold on. Cosine of 90 minus or pi over 2 minus x is equal to sine. This one is a negative on the outside. With formulas that we're going to see in chapter 5, that's helpful. With chapter 5, you're going to eventually learn how to take cosine of a plus b. Cosine, what did you get? Cosine x, cosine pi over 2. You're going to learn how to rewrite something like this. The property I was saying doesn't match because it's not minus inside. My property didn't work. But the property or an identity that you're going to learn in chapter 5, we can take cosine of a plus b and make it cosine of a cosine of b, plus what the negative came in, sine of a sine of b. At which point we would say cosine of pi over 2 is 0. Sine of pi over 2 is 1. How is that still not? Oh, my identity. Cosine, the signs change. Sorry, my bad. It would have been a minus times a negative. I killed the seal. There we go. So then 1 sine x plus 1 sine x is 2 sine x. But don't worry, you didn't have to. They didn't tell you to solve it. Because you couldn't. You don't know this property yet. Cosine of a plus b is co-a, co-b plus minus sine a, sine b. So all they said was graph the two, and hey, guess what, guys? They're equal, and we'll figure out someday how to actually show it. Long story short. Number 76. There we go. They were just showing you that, and this was what we practiced at the beginning of chapter 4, I think, or beginning of 4.5. If you multiply a trig by another function, if you divide a trig by another function, it's going to be dampened. It's not going to end up going forever and ever and ever at the same heights. So that's all they were trying to show you. And then the little arrows were just saying, hey, what's going on as you go to the right and as you go to the left? Well, as you go to the right, he's going to get lower and lower and lower. It's going to go to 0, like a pebble on the pond. And the ripples from the pebble. And this one, same thing. As I go to the right, it's going to go to 0. They actually had me coming in towards 0, though, and as I come in towards 0, it's 0 as well. Which is kind of funny, because if we divide by 0, we might not understand why that's true. Calculus could, but you guys might be a little lost on it. I think that's it? Oh, no. This was a word problem, yeah? Word problem, we were supposed to get d by itself, which is 27 over cosine, which is also 27 secant. And then they just asked us to graph it. But you would have wanted to, guys, when you graph, what do you do with this? What did you do with this? What should you have done with that? Yeah, the window. Make your x min and x max to be negative pi over 2 and pi over 2. That's how you would have had this exact picture. But the y's, because of this 27, the y's are going to be really high. So you might have had to make your y max something really high. But your x's should have gone from x min to x max, the interval that they gave you. Remember, 90 had us doing some more approaching. So let me get a graph really quickly. Does anybody have a question under 90? How was it not that bad? Yeah, you were allowed to use your graph. And as you do, pi over 2 is an asymptote. Here's doing the behavior around the vertical asymptotes, back from chapter 2. And that's actually where it's supposed to be. Then we have the tangent coming over here. So this little plus means from numbers a little bit bigger than, so pi over 2, numbers a little bit bigger than, my function's going down, negative infinity. Value's just a little bit below, the negative just means a little bit below. Oh, my function's going positive infinity. Negative pi over 2, numbers a little bit above. Oh, my function's going to negative infinity. And then negative pi over 2, numbers just a little bit below positive infinity. So, basically saying check the behavior near the vertical asymptotes. Done. Alright, cool kids. Anything left that we want you to talk about? Evens or odds? Oh my goodness, these were huge. Took a lot of space. 51? Okay. Anything else besides 51?
Just a question.
Yeah.
For the ones where you have to like determine whether it's even odd or neither, how do you determine that? There's 57, 58, and 64.
Oh, in your notes, go check out, let me remember. We wrote these down, the even odd properties of trig. I think it was section 3. I'm going to check real fast. I think it was after. No. Unit circle? There we go. You want to look at even and odd. You want to look at section 4.2 at the very end of notes. There was an even odd table where we said cosine is, secant is, sine is. So that's one place. One place is to go back and remember who we said was even and who we said was odd. But another place, do you remember, Melanie, how even and odd kind of has to do with symmetry? Okay. So since even and odd has something to do with symmetry, what we could say when they give us a problem like, you were saying 57, even, odd, or neither, they're actually telling us to think about the graph. So for instance, if I was to think about tangent, it comes up. What kind of symmetry is that? Not y-axis, not x-axis, but origin. He's odd. Odd origin goes here. But if we were to look at something like, is he up here? Secant. Secant bounces off of cosine. I can't change colors up here, but if you look at secant, doesn't he have y-axis symmetry? He's even. Now, some of these got a little bit harder. They got beyond the normal graphs. But as you went to some of these harder ones, look in your graphing calculator. So then you graph it. And then verify algebraically. Okay, so when you actually graph, I think with these ones, I would have told you to use your calculator. I would think you graph these like you can look at the graph in your calculator, look at the y-axis, look at the x-axis, and say, does it fold across the y? Then it's even. Does it fold and then flip? Just take one little part. Tangent keeps going forever, but it gets hard as we get further away. Start with one little part. Does it fold over and down? Odd. Or does it not have either? Neither. Okay, does that make sense? Yeah. Since I'm right here, let me go back to number 51 to try the question on real quick. He's right up here. Use a graph to solve the equation on the interval. This is really similar to the one we looked at with the
58.
56, yeah. It's really similar to that one. So what you could do to get decimal answers is you could make cotangent y1 in your calculator. Graph cotangent. You could graph negative root 3 over 3 as y2. You would make your x min and x max negative 2 pi to 2 pi, and you could find your intersections like this one showed. Find where they hit each other. And those x's would be the answers. The other way to solve it, though, is like, wait a minute, hold on. Cotan flips tangent, right? If cotan flips tangent, unit circle would say, well, that's going to happen when tangent's in, you know. Cotangent will be negative root 3 over 3 when tangent is, what's that other one that tangent can equal besides root 3 over 3? Square root 3 over 3, 1. Square root 3. It's going to happen when tangent is the other one. If we were to flip that and simplify, tangent is the reciprocal. If we were to flip it and simplify, it would end up to be negative root 3. So we can think of our unit circle and say, okay, tangent is negative in the not tangent. It's going to be negative in quadrant 2 and quadrant 4. Square root 3 over 3, 1 square root of 3. Tangent's going to be root 3 at pi over 3. So we can take the pi over 3 angle in the second quadrant, which would be 2 pi over 3. We take the pi over 3 in the fourth quadrant, which would be 5 pi over 3. We could also get there by going negative pi over 3. And we could go negative 4 pi over 3. There's two different ways, getting there positively or getting there negatively, to get to both of these places where tangent will be root 3, cotangent will be negative. So both ways work fine. One way is just to graph both and find intersections. They'll be decimals. The other way is to think unit circle. What do we know? When does that happen? And steal those as your answers. So, the nice thing is, section 4.7, we have to get better at going from an answer to an angle, and that's exactly what we're going to practice with inverse trig. So I think most of the ones that I heard you guys with questions on or that I took time to review, the trick was, wait a minute, I'm going backwards, I'm getting an angle from a value, that's inverse trig. So let's go ahead and undouble check in. No more evens or odds?
Number 22.
It was a graphing one, right? Okay. So before we leave section 4.6, I don't mind, let's do one more quick graphing one. You guys help me out with how you did it. If you want to have your bell work, sorry, not your bell work, your spiral open to number 22, you can actually show me step by step, or you can close it and say, okay, do I remember what I did? Number 22, y equals 3 cosecant of 4x?
Yeah.
Okay. I'm not going to put random people on the spot. That's kind of hard if you guys haven't had time to talk about it. Not all of you might have gotten it in homework. So let's just call out answers. Cosecant is 1 over who?
Sine.
Okay. So I want to look at sine. Why am I putting a 0 plus?
Because we're not shifting up.
Good. And why am I doing x minus 0?
Just to know your initial point.
Yeah, we're not shifting right or left. We're not shifting up or down. So when I go to make my sine curve, I know my sinusoidal axis. Yeah, it's oscillating right here. Hasn't shifted. Its initial point will be, how do I know it's going to be right there? It didn't shift, x is 0, and it starts in the middle, so it starts on the sinusoidal axis. Now, how high, how low is my sine right
4, 3.
Yeah. So I'm going to go 1, 2, 3, 1, 2, 3. The last thing I can deal with is, what's the period? How do I find period? Yeah, 2 pi over 4, or sorry, 1 over 4 times 2 pi. Either way, you get pi over 2, which is good and all, but what else should I probably think about? So if I'm repeating every pi over 2, what do I want my units to be? Let's go by pi over 8, yeah? My tick marks will be pi over 8. In 4 of those tick marks, I'll complete a set. So if I'm starting at 0, because my initial point is 0, let's go by pi over 8. So 1 pi over 8, 2 pi over 8, which is pi over 4, I think, right? 3 pi over 8, 4 pi over 8 would be pi over 2. now my key points, I just need to go 1/4, I'm at the max, another 4th, and in the middle, another 4th, at the bottom, another 4th, and back up. I'm going to change colors right about now, because that was all the foundation. So now what do I do for cosecant? I bounce. Well, it's kind of easier if we get the vertical asymptotes then bounce, because then we know how to hold it in. So when do vertical asymptotes happen? Every single intercept. Careful saying x, you're right on this one, but technically it's sinusoidal intercept, right? But this time the sinusoidal is the x. And then yeah, let's bounce. But we bounce and we meet at the max and mins, right? We bounce and then we meet at the max and mins. Okay? Good review.
When you go from cosecant to sine, why would it be 1/sine?
Oh, it is 1/sine. But the 1/, is what happens when I bounce and when I do the vertical asymptotes. So I'm just looking at what if it was sine, and then the 1/, is when I bounce, when I do the vertical asymptotes. I'm dealing with the 1/. Okay. Keep trying. It's cold here, my hands are freezing. Okay. He looks tired though. Does anybody else get colder when they're tired? I do. Everybody tired?
No, when I'm warm, when it's warm,
When I'm warm, I knock out.
I'm
When I'm
just
here, I get cold easily when I'm tired. When it's warm, I get tired too. Like when it's warm, I get tired, but when I'm tired, I feel cold easily.
It's easy to get
I'm
cold.
just always cold.
Yeah, right? Like when you're tired and you wake up, you're just like,
It
it feels like 5 o'clock and then yeah,
I feel like in general, I'm just tired. Just waiting. I'm just waiting.
alright, let's hope we can go home.
I'm always tired.
People who don't understand are going to be entertained by our
It's
reflections.
so
Oh, great.
stay focused.
They'll come in making fun of us tomorrow. Alright, here we go.
Are gonna be like,
4.7. We're saying hi. We're saying hi to future people. This is so weird. Okay. The past means the future, the present means the future. Tired?
If you really think about it, like, I think all of our students are actually gonna watch the video, they're just gonna wing it.
They can technically, they save the notes online, so you can just copy them down.
Ryan's gonna be the one that's gonna listen to
AKA, hi Ryan. Okay, so, section 4.7. There's some other time. I D might. I put it on like double speed though. I put it on double speed.
This is Leon, you put it on double
Oh,
speed,
no,
just like
don't
you
talk
just.
about those videos.
Alright, here we go. We talked about yesterday how inverse takes the normal and reflects it, right? But what's the dilemma when you take any any of our periodic trig functions and we flip them, what are they all gonna fail? The vertical line test. So the original fails the horizontal, which means the inverse will fail the vertical. Oh, it's not a function. The calculator can't do it because it's going to have infinitely many answers. But I had you yesterday type in second sine, and it didn't have infinitely many answers. It just had one. And the reason is we restrict sine to find what we call the principal value, which will always be in between. We have to restrict it so that it doesn't fail. If I went any farther, it would fail the vertical line test. If I went any farther, it would fail the vertical line test. So we cut it off to where it doesn't fail the vertical line test. The inverse doesn't. But that cutting off is going to restrict what answers we're looking for the principal value. But once we find that, we could find all the others if they ever ask us to, but the original first answer is going to be just one, which is why on this page, you guys were all packing up, and I was like, wait, so much time. On this page, we went ahead and peeked at a few examples real quick to say, okay, so we're taking values, we're taking answers too. Guys, look at the unicycle quiz. This is great timing. What's being put into arc sine or sine inverse? Remember I said they're synonymous. What's being put in? Angles or ratios? What was being put in, or what is put into normal trig? What are these? 2 pi over 3, 5 pi over 4, 11 pi over 6. What are all of these? Radians, and radians measure angles. Angles get put into the trig, and what comes out? So it's over HPrecalc. Opposites over hypotenuses, adjacents over hypotenuses. Ratios of sides come out. Angles go in. So angles go into normal trig. Ratios come out. But inverse trig, that's true. Too focused taking notes. Give me a second. Regular trig is right behind me on the board for the unit circle quiz. Angles go in. Ratios of sides come out. When you get to the inverse, ratios go in, and what comes out? Radians, or what do radians and degrees both measure? Angles. So inverse, you have to flip what goes in and what comes out, which means we're going to have to know our unit circle backwards and forwards. You have to know if I give you cosine of 2 pi over 3, you get negative 1/2, but cosine of negative 1/2, ooh, that's 2 pi over 3. I have to know it backwards and forwards and backwards. But wait a minute. Well, hold on, before the wait a minute. Let's fill in a couple blanks. Inverse sine. Normal sine. You plug in to normal sine, you plug in an angle in radians or degrees. If you guys, I feel like a lot of you are thinking radians, degrees, which is good. You just got to attach it to, oh yeah, that's an angle. What you put into sine or cosine or tangent, any of the trig, what you put in is an angle. What you get out is a ratio of sides. Specifically with sine at the opposite over hypotenuse. So, for inverse trig, whether you see it with a little -1 notation, which we've talked about, it gets kind of confusing, or whether you see it in its alternate form, which doesn't have a -1, maybe a little less confusing, doesn't have a superscript I need to type, maybe a little easier. Arcsine, they mean the same thing. Whether you see sine inverse or arcsine, both of them, you're putting in the ratio of sides. You're putting in the ratio of sides. And you're getting out angles. You're putting in ratios of sides. And you're getting out angles. It flips. It flips. And a quick reminder, sine inverse is not a reciprocal. It is not cosecant, which is why you were never allowed to use second sine to find cosecant. We always had to, in our calculators, do 1 divided by sine. Otherwise, we do 1 divided by sine. Now, this little part over here is the domain restriction. The domain restriction from the page before. The restriction that allows the calculator to give you one answer even though there are infinitely many places this can occur. Which is why, when we said arcsine of -1/2, hold on, pause. Can you guys go to section 4.2? Use your table of contents. Go to your unit circle. That should be all drawn out. Could be on a pad of paper, you could just draw it. Section 4.2, go find your unit circle. Look at all the y's of all the points. Look at all the y's of all the points. When are the y's -1/2? Third and fourth quadrant at what angles? Exactly. Sine, aka the y, is -1/2 at 7 pi over 6 and 11 pi over 6. So my question to you is, wait, if sine is -1/2 at both of those places, why are neither one the actual answer? The unit circle shows you the y, or the sine, is -1/2 at 7 pi over 6 and 11 pi over 6. Why is neither one the actual one principal answer? Which means backwards. Those are both angles where the ratio is true. Look at the green circle. How positive am I allowed to go in all my answers? Only the half pi. 7 pi over 6 is way too big. 11 pi over 6 is way too big. But guys, 0 to pi over 2, sign is positive there, not negative, so I can't even use any of 0 to pi over 2. So then, okay, negative pi over 2, that's going the other direction. Do I hit somebody?
Yeah.
And how do I hit it? By going negative pi over 6. So you can get to angles where this is true, where sine is negative 1/2. You can get there by going 7 pi over 6 or 11 pi over 6, but I have to have just one principal answer to start with. The calculator has to be able just to give you one, and we have to say, okay, what is that principal one? And to do that, you can't go beyond pi over 2, so I can't look at either of those two. But I can say, hey, let's go the negative direction, and oh, hey, I hit that guy by going negative pi over 6. There's more than one way to arrive at an angle. We have to figure out the exact way that they're asking whenever they give us an inverse trig. So in letter B, how come it was just pi over 3? Why don't you have to do something crazy with that one?
It's not negative.
Yeah, it's not negative, so I'm allowed to go in the first quadrant. When we go in the first quadrant, we're going to hit pi over 3 before pi over 2, so we're good. The unit circle says pi over 3. If you look on the y's, if you're still on the unit circle, at pi over 3, the y is root 3 over 2. Cool. We hit it before we get to pi over 2. It's legal. Go. But why is this one DNE again? In your unit circle, the biggest y gets is 1, and the lowest y gets is negative 1. It will never reach tangent.
Can you work a domain restriction, not a range restriction?
It's a domain restriction of inverse trig, because the y's of the inverse are the inverse. But in a normal trig, it would be a domain restriction before we flip, before we do the inverse. It'd be an old domain restriction, because the x's used to be angles, but now the y's are angles. Does that make sense? Oh wait, pause! Ah, calculator, go! Sine inverse of 0.265. Sine inverse of 0.265. Jonathan, say yours a little bit louder.
0.2682.
There are two different answers possible. Did anybody else naturally get a different one? Good, Janelle, 15.1. 367. And those of you that got one, figure out how to get the other. It depends on what mode. If Janelle goes to her mode, she's in degree mode. Those are degrees, 15.367. Jonathan, if you go in your mode, you're in radians. How do you know which one's right? I don't know. Either they tell you, or you just pick one and then look at the back and see which one they actually want. Sometimes they'll have both answers, because when they give you a ratio, guys, ratios don't have units. Ratios don't have units, so there is no special way of looking at a problem and knowing which one they want. So, if they want radians, they better tell me radians. If they want degrees, they better tell me degrees. And if they don't care, then fine, I'll just do whatever one I want. Okay? But if the back of the book has the other one, okay, change your mode and then see if you agree. So that's something I just need to point out. If they don't tell you what kind of angle they want, whatever. Choose the one that you want. So, if we can do inverse sine, guess what else we can do? Inverse cosine and inverse tangent. I'm going to go pretty quickly on these ones, just because we kind of got the idea down on sine. We're going backwards for sine inverse. Taking the values, needing to match them to the angles. If they're looking just for one answer, we have to figure out what right way of writing the angle. Which right angle to choose. Cosine. Plain old cosine. Starts at the top, goes to the bottom, comes back to the top. He fails the horizontal line test just like sine does. So we have to cut him just like we cut sine. But the tricky thing is to cut him. We're not going to cut on either side of the axis because that would fail the horizontal line test. we have to start at 0 and go to pi. Think kind of like the vertical asymptotes for secant. So to kind of measure up. For cosine, we're going to do a domain restriction of cosine, which is going to translate in a range restriction for the inverse. Does that make sense?
Yeah.
What was the domain is now the range when we're talking about the inverse. Once again, the reason we have to do this is because if we flip cosine, he's going to fail the vertical line test also. So I have to only choose one piece to use. And that one piece is going to, back with cosine, the domain was just between 0 and pi. The range was in between -1 and 1. For the inverse, everything flips. So now the domain is in between -1 and 1. So that's why the picture. What was on the y is now on the x, and what was on the x is now on the y. And technically, I think I was color coding green on the page before, so let me put it in green. But long story short, what do you need to focus on? Cosine inverse answers just between 0 and pi. Which if you want to think in the unit circle, if you're looking at your unit circle, looking for when the x or the cosine equals, we're just looking at quadrants 1 and 2. For sine inverse, we were looking positive pi over 2 and negative pi over 2. We were looking in quadrants 1 and 4. But for cosine, we have to look in quadrants 1 and 2 in order to make it legal, in order to only have one answer per question posed. Inverse tangent. He's negative pi over 2 and pi over 2. And he repeats. But even though tangent repeats, if you guys look at one cycle of tangent, if you just took one cycle, doesn't one cycle pass the horizontal line test? Just one. Oh. So we're not going to like strangely cut it. Tangent, we're actually going to cut it in a pretty natural way. We're just going to take one cycle and say, oh, hey, we only want one again. So if we flip that one cycle, just that one and ignore the rest, we'll be fine. The inverse will pass the vertical line test. So in the old tangent function, the domain would be negative, oh, I can't do a closed bracket. There's a vertical asymptote there. I apologize. Open parenthesis. I'd have to go between negative pi over 2 to pi over 2 to make the original pass the horizontal line test. The range, though, well, tangent goes forever low, forever high. That's going to translate into the range only picking angles between negative pi over 2 and pi over 2. Okay, it's like sine inverse, kind of. The domain's going to be my forever left, forever right. An inverse tangent. Something like tangent, just, well, flipped. Just flipped. With now y equals pi over 2. And negative pi over 2. With y is equaling pi over 2 and negative pi over 2. So what quadrant is tangent going to be looking at? Zero to pi over 2, what quadrant is that? And 0 to negative pi over 2, what quadrant is that? And then guys, if you ever did need to do a cosecant inverse or secant inverse or cotangent inverse, well, we'll talk about them. But basically, we need to think about sine, cosine, tangent, but remember, oh yeah, the values flip. The ratios flip. How would that work? We'll talk about it soon. The one thing we didn't get to write down, let me go back to sine real quick. I showed it on inverse cosine and tangent. I didn't technically show it on inverse sine. So just in case it helps, this restriction for sine, what quadrants is that again? Yeah, 0 to pi over 2 is quadrant 1. 0 to negative pi over 2 is quadrant, quadrant 4. Sorry, quadrant 4. Quadrant 1, quadrant 4. So long story short, cosine and tangent. We plug in. You guys look up there on the board. Cosine of, tangent of, radians, angles. We plug in angles to normal trig. Angles in degrees or radians. And what do we get out? Ratios. So normal trig, you plug in angles, you get out ratios. Inverse trig, inverse cosine, which can be written just like sine, can be written with a -1, or it can be written arc cosine. Or inverse tangent, which can be written tangent -1, tangent inverse, or it can be written arc tangent. When you go to inverse, what goes in will be ratios of sides. So what comes out will be angles. Maybe the arrows are more complicated than they need to be, but long story short, normal trig, angles go in, ratios come out. Inverse trig, ratios go in, angles come out. So when you see tan inverse of -1, first of all, domain restriction. You guys look at your notes. Tangent inverse, what do I need to be thinking about as far as what's coming out? What angles am I allowed to look at? Quadrants 1 and 4, but what angles? Look at, we just wrote it down. I circled it in green. Oh, not 0 to pi, tangent. Careful. That was cosine. Yeah. You gotta look in between -pi/2 and pi/2 if you want to think about it in unit circle. We're looking between quadrants 1 and 4. And we're looking for when tangent is -1. We don't see the tangent on the unit circle. We only see x's and y's. Help out cheer chart people. Anybody out there? Tangent will always be 1 or -1 at 45s. So what 45 do I want? The first quadrant one, where tangent is positive, or the fourth quadrant one, where tangent is negative? But am I going to write it 7 pi over 4? No. How am I going to write it? Negative pi over 4. And if you were to do in your calculator second tangent of -1 in radian mode, you would get a decimal that, check it, equals pi over 4 times a negative. It is the one answer the calculator can give you. I think the remember is just not reciprocal. Inverse is not reciprocal. I think that's all I was going to say. So this, not secant. This, not tangent. No, no, no. It just means go backwards. So okay, what if I was to give you something like, I don't know, cosine inverse of 1.4. Have to use a calculator, right? That's not 1/2 or √3 over 2 or √2 over 2, 0 or 1. So how would you do it? Yeah, plug it in. Second cosine of 1.4. The answer is DNE. Where are you guys? Are you alive?
Yeah.
Why is it none? Why is it DNE?
Oh,
Cosine can never be bigger than 1 and never be lower than negative. Good. Look at you guys. I had you going for a while. Those of you that figured it out before I said it, good job. Cosine cannot be bigger than 1 or negative 1.
No.
But what if I was to ask you for tangent inverse? Can he be bigger than 1?
Yes.
He goes to infinity and beyond, so yeah, he can be whatever you want him to be. So, who's plugged that in here? Second tangent, Rebecca is, I think Jonathan is, Janelle is. Whoever gets it for me first.
0.9505.
What do we got?
0.9505.
9505. I'm guessing that Thomas is in radians. Anybody in degrees?
54.26.
Both answers are just as good, and as long as they don't tell us which one they are. Struggle. All right. We
Should we start doing that?
have more to finish tomorrow, which is okay. So we continued on 4.7. I think our calendar actually has 4.7 not due until Friday, so I think we're okay. Kiddos, I will work on 4.7 tonight, but you don't have to finish it because we're not all the way done. I'll see you guys later. Go have happy nutrition. Carl, I'm trying to get it up. There we go. Let me pause the video.